Hello, today we're going to look at water's properties and how they pertain to acids and bases. So in the previous lesson we defined acids and bases, we talked about the various definitions for acids and bases, and we tried to talk about, or I tried to explain, conjugates and how the conjugate pairs work. So in this lesson what we're going to look at is a little bit more water, because what happens with acids and bases is they're always going to be taken, we're always going to be working in water. So we need to look at some stuff about water before we can go any further. First of all, we're going to look at what's called the auto-ionization of water. Now, water by itself, before we even add any acids and bases in there, is going to have two water molecules that are going to react together. So we're going to have two water molecules in the solution at any time. What's going to happen is that these two water molecules can actually attract each other and kind of react. Because don't forget, water has that hydrogen bonding in there. What's going to happen is these two water molecules are going to come near each other, and this hydrogen here is going to be attracted to this oxygen. And as a result of that, it's going to actually pop that hydrogen off, and this hydrogen is going to actually move over to this one here. And what we're going to see is that is actually the definition of an acid-base reaction. Notice what happens is what I'm left with afterwards is I have the hydronium ion, because I have H3O, and what I'm left with is the OH. So what's going to happen here is I'm going to have the reaction forming, and I'm going to get H3O plus, and I'll have hydroxide. This happens all the time in molecules of water. And what happens is there's an equilibrium, because as soon as these are made, they're going to break back down and go into the reactants again. So we have an equilibrium between these two states. This is what's referred to as amphoteric. Now stop and think about this before I define amphoteric, which already right there. We need to look at whether we have an acid or a base. Now if we think of this one as the substance that is losing the hydrogen ion, this would be considered the acid. This would be the one taking the hydrogen. Because think about what's happening here. One is losing, the other one's gaining the hydrogen ion. That is the definition of acids and bases. The one gaining is considered the base. The one losing is considered the acid. Okay? And what it leaves behind are the conjugate pairs. Okay? So what we have is water acting as an acid, water acting as a base. Okay? Now, as a result of this is what's referred to as amphoteric. Anything that can act as an acid and a base is referred to as an amphoteric substance. Another example of an amphoteric substance would be something like HCO3 minus. Because what it can do is it can lose a hydrogen ion and become CO3 minus 2. Then it would be acting as an acid. Or what it could do is it could take a hydrogen ion and become H2CO3. So it has two options. It can either, so this would be considered an amphoteric substance, because in this direction, when it loses the hydrogen ion, considered an acid. When it gains a hydrogen ion, it's considered a base. So therefore amphoteric. If we take a look at that carbonate ion, CO3, 2 minus, well, it can gain a hydrogen ion. And when it does, it goes back to that CO3 minus. So it's acting as a base because it's taking a hydrogen ion, but it cannot lose any more hydrogen ions. So this is not amphoteric. So it has to at minimum have a hydrogen in it in order for it to be amphoteric. Okay? So amphoteric means it can act as an acid in one scenario and as a base in another scenario. Now back to the water autoionization. That's what's going on here. So the autoionization of water. Now remember, water is a liquid, and water here is a liquid. This is an aqueous ion. This is an aqueous ion. So I can, if I understand my rules for equilibrium, what I can do is I can write what's called equilibrium constant for this. We're going to put a little w down here because we have an equilibrium for water. That's what the W stands for. And we're going to write the products over the reactants, which would be the concentration of H3O plus, the hydronium ion, and multiply that by the hydroxide ion, all of that over water. But those are liquids, so we don't put them into the equilibrium. So what we have is Kw is equal to the hydronium ion times the hydroxide ion. All right? This is an equilibrium that we find in all water. And when we look at this and we actually look up the magnitude of Kw, we find that it's 1.0 times 10 to the minus 14. Now you know something about Ks, and you know something about equilibrium positions, right? Does this reaction favor the products, or does this reaction favor the reactants? Well, since K is so small to the negative 14 to the negative 14 power, this reaction does not favor the products at all. It heavily favors the reactants. So in pure water, would I expect a lot of these ions? No. I'm going to get a very, very small number of these ions in the water. Okay. Now, this Kw has a name for it, and this Kw is referred to as the ion product for water. So this is the ion product for water. Why is it the ion product? Because it's talking about the ions of water, and we're talking about a product because we're multiplying these two together. So this is the Kw, or the ion product for water at when it's at equilibrium. All right. So what we can do is we can actually use this to find the concentrations of these two ions, which we'll do in just a second. Before we get to that, though, let's take a look at something else. Now, remember we talked about before how the hydronium ion, okay, that H. Let's get another color here. That H3O plus, okay, is equal to our hydrogen ion, remember? So what we're going to do is we're going to see a little shortcut here. What we're going to do is we're going to get rid of one of the waters, and we're going to remove water from this. So we can say that what happens with water is that the water molecule, which is a liquid, is going to break up into hydrogen and hydroxide ion. So this is one other way you might see this reaction. So I'm just rewriting this reaction in another format. And when I do that, my Kw is equal to the hydrogen concentration times the hydroxide concentration. So this is just another format for Kw, which is equal to 1.0 times 10 to the minus 14. Okay? Oops. All right, so there's our equilibrium expression. Now, one thing I can do with this, let me erase some of this stuff here real quick, is I can use this to solve for the concentration of hydrogen. So let's say we have pure water, and we want to look at what the concentration of the hydrogen ion is. Now think about it. If this breaks down, I'm going to get one of these, I'm going to get one of these. So however many of these I get in solution, they're going to be the same, aren't they? Wouldn't you say that the hydrogen, try clicking the pen here, the hydrogen concentration, the concentration of hydrogen ions would be equal to the concentration of hydroxide. This is in pure H2O, right? Because every time the water breaks down, I get one ion, and it breaks down again, I get a hydrogen or hydroxide. So it breaks down, I get one of those and one of those. So therefore, if I said that the concentration of the hydrogen ion were equal to X, I could say that Kw was equal to X times X, or X squared, right? Which is all equal to 1.0 times 10 to the minus 14. So therefore, what I can do is I can say that X is equal to 1.0 times 10 to the minus 7. And that would be equal to the hydrogen concentration. Since it's a concentration, I'm going to rewrite that with a molarity in there. So 1.0 times 10 to the minus 7 molar. So in pure water, when I have just water by itself, the hydrogen is equal to the hydroxide. That's our definition of neutral, right? Our acid is combining or equal in concentration to the hydroxide. That is a definition of a neutral solution where these two are equal to each other. And in this case, both the hydrogen and the hydroxide are going to have the same concentration. They're both going to be 1.0 times 10 to the minus 7. It's a really small concentration. It's 0.0, with 6 zeros before you get to the first one. So very, very low concentration of hydrogen ions. And an equal concentration of hydroxide would make the solution basic. So what I'm doing here is I'm deriving the definition of acids and bases. In this case, our definition of an acid is really based on water. So in pure water, the hydrogen concentration is equal to the hydroxide concentration. We would say that the solution is neutral. So as long as this stays in balance, as long as the equilibrium of water, the dissociation of the liquid water into hydrogen ions stays the same, then I would have a neutral solution. But when we have an acid or a base, our concentration of hydrogen ions doesn't stay equal. It's not equal anymore. one of these is going to be higher in concentration. So if I were to add hydrogen ions, if I added HCl to this, remember HCl breaks up into hydrogen ions and chloride ions. Well, if I put this into the water, isn't the concentration of the hydrogen ion going to go up? Right? This goes up. So if we look at Kw, Kw is hydrogen times hydroxide. And if this is a constant and it has to say 1.0 times 10 to the minus 14, and I make this go up, wouldn't this have to go down? And therefore, this would be true. All right? My concentration of the hydrogen ion would be greater than the hydroxide. And if I added more hydroxide, then the opposite would happen. This would go up and this would go down, and that's what we would call a base. Okay? So what we can do is we can use this to figure out the concentration of hydrogen ions and hydroxide and determine if something's acidic, basic, or neutral. So let's take a look at number 1. What I want to do is calculate the hydrogen or hydroxide. Well, if I know that my hydroxide is 6.7 times 10 to the minus 5 molar, what I want to do is I want to find my hydrogen concentration. So what is the concentration of the hydrogen ion? What I'm going to do is I'm going to use Kw is equal to hydrogen times hydroxide. And what I'm going to do is solve for my hydrogen ion. Hydrogen concentration is equal to Kw over my hydroxide. Now, Kw is equal to 1.0 times 10 to the minus 14. That's always going to be true. You're never going to have that number change for you. Your hydroxide is 6.7 times 10 to the minus 5 molar. So what I can do is I can find my concentration of hydrogen ion by just solving this little equation here. I end up with, when I do the calculation, the division of this, I end up with 1.49, which is, no, let's take that back. Let's just round it to 5. 1.5 times 10 to the minus 10. And this would have molarity because I'm looking at concentration of hydrogen ion. It would be the molarity. So the question is, now is this solution acidic, basic, or neutral? Well, since my hydrogen ion, you want to look at it this way, is less than my hydroxide ion, I would say that this solution is basic. Okay? You could also compare it to 7, because remember at neutral, the hydrogen ion has to be equal to 1.0 times 10 to the minus 7. That would have to be the hydrogen. The hydroxide has to be the same number, right? If it's neutral, these two, this is the only time that these two numbers are going to be the same, is when we're neutral. Well, if my hydroxide is greater than -7, the hydrogen has to be lower, and therefore I could also conclude that it's a base. So there's two ways to determine if it's acidic, basic, or neutral. Compare it to 7, or to 1.0 times 10 to the minus 7, or compare it to the hydrogen hydroxide. Notice what I'm doing here is really comparing it to the 7, and that's where pH is going to come in our next lesson. So let me do it one more time here. I know there's 4 examples, but I'm only do one more example here, and we'll do more in class. So let me erase this, and I'll do the second one, and then I'll take questions in class. All right, so number 2 is I have the hydroxide. Again, I'm looking, let's do number 4 just to solve for the other one, because I have already solved for hydrogen. So let's solve for hydroxide. So I'm looking for hydroxide concentrations. Okay, so I'm looking for the molarity there. I'm going to use Kw is equal to hydrogen concentrations times hydroxide concentrations. So my hydroxide is going to be equal to Kw over concentration of hydrogen ions. Plug in 1.0 times 10 to the minus 14 over my hydrogen concentration, which is 3.45 times 10 to the minus third. And when I plug that in, I can figure out what my hydroxide concentration is. And when I plug everything in, I end up with 2.9 times 10 to the minus 12. And I probably should go 3 significant figures because of this. So if I want to, I'm going to change that. I'll make it 2.90 times 10 to the minus 12. And that would be molarity. So my hydroxide is to the minus 12. And my hydrogen ion is to the -3. So which one is a higher concentration? Clearly my hydrogen ion. So therefore I would say that this solution is acidic. Again, I could compare that -3 to the -7 here and say, well, my hydrogen ion has to be greater than when it is neutral, so therefore it has to be an acid. Okay? All right, so there's two ways to figure out acid, base, and neutral, and you can calculate now your hydrogen concentrations and hydroxide ions when we mix up and have solutions that are not just pure water. All right, so I'll see you guys in class. Thanks.